Hi everyone, and welcome back to AOA. For month 4, we'll be talking about hashing functions, different data structures that incorporate hashing, and their uses. So as an overview, we'll just be talking first about what hashing is and some applications that hashing has. We'll be talking about dealing with collisions, which are problems that occur with imperfect hashing functions. And we'll talk specifically about hash sets, hash maps, and tree maps. So first are hashing basics. Hashing transforms a given key to another value, which is usually an integer of fixed length. And if you input any given key, you might not exactly know what it will yield, but it will definitely yield an integer of the size that you want. And aside from just strings, you can also put in images, videos, and more. And hashing is usually used with a hashing function, which takes one input and spits out one output. This is pretty important not only for data structures that we'll be talking about today, but also for larger concepts such as cryptocurrency in general and blockchain. So as you can see with the inputs on the left of the image, that as you input different strings, it'll return a different hash, and that's an important concept because we really want each string to hopefully return a unique hash. Hashing functions work primarily by giving an input key and turning it into an integer value through some algorithm. And hopefully this works for all inputs of that type and converts each key to a unique value. So some notable hash functions include SHA-256, which will take some string and turn it into some return, which is an integer. So if we put in Bob, we would expect a unique value from a given hash function, and we'd want no other string to give us that same value. If a hash function returns a separate value for every single possible key, that's called a perfect hash function, and they're usually pretty hard to find. And they're almost impossible to use because computers have limited memory, meaning that they can't have infinite hash values that they can store values in. So for example, if we wanted a hash function for integers and we had, let's say, 7 available spaces of memory, we'd have hash value is equal to the integer mod 7. And this wouldn't be a perfect hash function because if we put in 7 and 14, that would return the same value, which we don't want. And you can see a more optimized version of this hash function down here. So hash tables are a very basic data structure that uses hashes. You use hashes like indices, and the way that you interact with that is by using keys. You pass a key into a hashing function, which will return an index, and you store data there, usually in key value pairs. Collisions are when two different keys are mapped to the same value. So as we talked about before, when the hash function isn't perfect and returns the same value for both key inputs. For some real life examples, think about parking spaces or Chromebook carts if your school system uses those. For reasons we'll get into later, this is really bad for efficiency and security in data systems, so we want to keep collisions to a minimum. That said, since there aren't many perfect hashing functions, we need ways to address collisions. The two main ways are through open addressing and separate chaining. You can see an example of a collision on the right when John Smith and Sandra D both map to the hash 02. Linear probing is the most basic type of open addressing. This just means that when a collision occurs and you map two different keys to the same value, just go forward until you find a new position. So for example, you see that when you have collisions and you try to insert 47 here, which is the fourth insert, and then you collide with another value, which is 40, you keep going. So you go down to the sixth value of 76, but that's occupied, and you keep going again until you find the nearest open spot. And notice how you'll loop around if you run out of spaces. Another example is when you try to insert 55, when you hit the same problem where you're trying to insert where there's already a value. Quadratic probing works a lot like linear linear probing, but quadratic would throw the values much farther away. So instead of adding 1 over and over, you'd add 1, then 4, then 9 until you find an open position. And the reason that people use this over linear probing is if you throw the values farther away, hopefully there will be less clustering of collisions, meaning that you'll have less problems overall. This usually works best for larger arrays or larger memory because the idea is you want to throw it as far away as possible. Double hashing really doubles down on like randomizing collisions. You first pass your value into the main hash function and you try to insert it. And then if there are problems there, such as a collision, then you'll also pass it into a second hash value. That ensures that even if you have a collision, you can just add on the index of a second hash value and keep going. And if that is still occupied, then you'll just double the amount that you add on and keep going from there. Note that the table size has to be a prime number here, otherwise it doesn't work, as you can run into a permanent loop where you index by, let's say, 2 every time, and there's always going to be a value there. Separate chaining is a much more intuitive way to address collisions, and the idea is that if you have two values that have the same hash value returned, you simply chain them together by storing them in the same location. And this removes the need to actually throw the data farther away, but also leads to decreased efficiency, as we'll talk about later.
Last but not least, we can get into this new method called rehashing. So in the past, we've had issues where once you have enough values into your hash table, that can lead to some problems where you're going to have a lot of collisions. So one way to solve this is just to increase the size of the table once enough values are put in. So how this works is, for instance, you see right here where there's a table of size 5, but once the fourth value is inserted, the table doubles into size 10. So there's something called a load factor, or just the ratio of elements to slots before a table doubles. In Java, it's automatically set to 0.75, but you can change it depending on whether you value memory or efficiency more. So how it works is once the ratio exceeds the load factor, then the hash table size doubles and a new hash function is created. So see how in this diagram, the original hash function is mod 5, but once the table doubles, it becomes mod 10 because there are 10 elements in the table. After that, all the elements are rehashed and then put into new positions according to the hash function. So as we said before, a collision is just multiple keys being mapped to the same value. But there are several reasons why we want to avoid collisions and why when it happens, it's not a good thing. For instance, if you try to call for a key by accessing the hash value, and then you end up getting multiple possibilities. So this is like if you want to buy something from a vending machine, but you pick one number and that number has multiple different items that can be given. You want to ensure that you get what you want. And if it's not mapping one to one, then you could get some errors there. Next, there are cybersecurity issues. For instance, if a hacker can create files with the same hash value as the original data, that would replace and wipe out your old data. So that's why it's important to minimize the number of collisions, especially for cybersecurity. Last but not least, efficiency. So if the hash function is really poorly chosen and you use separate chaining, if the chain gets too long, lookup time reverts back to O of n instead of O of 1 because you would have to traverse through all of the elements in that chain in that position. On the other hand, if you decide to do open addressing and probing takes too long, then the insertion time will also take too long and approach O of n if the probing method is not chosen properly. So now let's go on to some applications of hashing. The first advantage of hashing is that the lookup time is extremely efficient because hashing just maps a key to a value the lookup time is O of 1, which will always be better than O of n or O of log n, because O of n grows linearly and O of log n grows logarithmically. So even though O of log n grows very slowly, it's always going to be slower than O of 1, which is just constant, whether there's one element, 100 elements, or a million elements. Next is memory efficiency. If the hashing function is created well so that there's very few collisions, this evenly distributes memory so functions run faster and everyone's happy, because that means that things run more smoothly and there aren't any inefficiencies or bottlenecks. Next is data encryption. Alex already covered this a little bit, but as we see here, hashing turns passwords into just an alphanumeric string of letters and numbers that look like gibberish if you don't have the key to decode it. This is really important because if, say, a hacker breaks into a website and is able to collect a bunch of passwords, if it weren't for hashing, the hacker would be able to access all of these passwords and mess with people's data. But thanks to hashing, if a hacker is able to access these passwords, the only thing that the hacker will get is this giant chain of strings, a giant chain of letters and numbers, which doesn't really mean anything if the hacker doesn't have the key to decode the hash. Last but not least, we have data compression. So like Alex said before, we can do hashing to videos and images. This is pretty important because if you're able to express files that take up a lot of space, such as videos, into these hashes, then it can shrink the size of the original content. And then using the hash, we can recreate the original file for usage. Next, we'll be talking about some other data structures that implement hashing. So first is the hash set. A hash set still operates much like a hash table, and it has the same benefits of extremely fast lookup and insertion time. The slight difference is that it stores data as objects rather than key value pairs. This is really important because set objects are unique, which means you can't insert duplicate objects that have the same value into a hash set. And while hash tables use the put method, hash sets use the add method. This is a relatively minor difference, but it's worth noting when you implement these in real coding. Next, let's move on to hash map. So like a hash table, it stores data as a key value pair. And the difference between a hash map and a hash set is that you can have duplicate values, but you can't have duplicate keys, because duplicate keys lead to collisions. The other thing about a hash map is that it's slightly faster than hash table and hash set for for reasons that we won't get into in this course, but it's mainly because a hash map uses a unique key, while hash sets have to refer to objects which is slightly slower. Next, we'll be going into tree maps. So tree maps are slightly different. They still use hashing, but unlike hash maps, hash tables, and hash sets, tree maps have O of log n lookup. The reason why they have O of log n lookup and insertion instead of O of 1 is because tree maps sort and store data in a set order that's whether it's alphabetical or numerical, which means that tree maps use a self-balancing binary search tree to sort and store the data. We'll be covering binary search trees in month 8 of AOA, but what you need to know right here is that tree maps are really useful if you're trying to store data that has a logical order of items. For instance, if you're a teacher in a school and you want to have a list of your students based on alphabetical order by like last name, then it would make sense to put the data into a tree map where it's automatically sorted. Finally, we have an example here of how to implement a hash table in Java. First, you follow this format of declaring your hash table, and then you can start putting items into the hash table. Now, this is what's really interesting. So when you print out the hash table, There are two possible results because a hash table, along with hash sets and hash maps, do not have any set order of which the data is stored in or printed out. Tree maps do, and that's why sometimes you would rather use a tree map and have a little bit less efficiency. But see here how there are two possibilities, and the more items that you put into the hash table, the more possibilities you have for the output. The code is very similar in terms of implementation for hash set and hash map. You change a couple of methods, but overall the formatting remains the same. That concludes our month 4 AOA video. Stay tuned for next month when we will be going over the basics of graph theory.